In this video, we are going to be looking at the Newton-Raphson's method of numerical methods in engineering mathematics. And specifically, we are going to be using this question to explain this concept. So in the first video, I explained that the Newton-Raphson's method is actually a method used in engineering mathematics to approximate the root of a given equation. Now, by formula, the Newton-Raphson method simply states that xn plus 1 is equal to xn minus f of xn all over f prime of xn. Of course, where xn plus 1 simply means the current iterative value and xn simply means the previous iterative value, or in most cases the initial guess, and of course f of xn simply means the value of the function at the initial guess, and f prime of xn simply means the value of the derivative of the function at the given initial guess or at the previous point. Now we are given this question 2x cubed minus 3x minus 6 to be equal to 0, and we have to solve this using the Newton-Raphson's method. So first of all, let us pull out our function. We have f of x to be equal to 2x cubed minus 3x minus 6, and this is equal to 0. So from the formula, you see that we have the derivative of the function. So which means we need to differentiate that given function. So we simply find f prime of x, which means differentiating this function. If I differentiate 2x cubed, I will simply have 6x squared minus, if I differentiate 3x, I will simply have 3. And if I differentiate 6, of course, that's a constant, that simply gives me 0. So we have this now. All we need to do is to look for our initial guess. So what we need to do now is to find our initial guess. So observe that in this question, you've not been given an initial guess. And I've said in all my iteration videos, to find an initial guess, what you do is simply you choose two values. These two values are labeled A and B. So our initial guess x naught is equal to A plus B divided by 2, where A simply means the value of the function of x that turns this function into positive, and B is simply the value of the function of x that turns this function into negative. And they are arranged in such a way that the function must turn directly from positive into negative or from negative into positive. So let's choose a scale of 1. So we can simply start with 0. If x is equal to 0, we can now find f of 0. That simply means plug x into this equation as 0. Okay, so if we do that, we simply have 2 into 0 to the power of 3 minus 3 into 0 minus 6. So this simply gives us negative 6, and this value is negative. So we move on to the next value, 1. We find f of 1. F of 1 is going to be equal to, so we have 2 into 1 to the power of 3 minus 3 into 1 minus 6. So if you do everything together, this is going to be 2 minus 3, which is negative 1 minus 6, and that's simply negative 7. Again, we have a negative value, and the rule states it must turn from negative into positive. So you move to the next value. After 1, we try 2. So f of 2 is going to be equal to 2 into 2 to the power of 3 minus 3 into 2 minus 6. Now this is going to be equal to 2 to the power of 3, of course, is 8. 8 times 2 gives us 16. 16 minus 3 times 2, that's 6. 16 minus 6 is going to be 10. 10 minus 6 gives us positive 4. So we see now that this is positive. So we see now that this value turns from negative directly into what? Positive. So this simply implies that our A is going to be equal to the value that caused the function to be positive, and that is simply what? 2. And B is simply the value that causes the function to be negative. In this case, it is 1. So which means our initial guess can now be found as 1 plus 2 divided by 2, which is actually what? 1.5. So our initial guess x naught is simply 1.5. Now, having found our initial guess, the next thing to do now is to obey the formula. Okay, we need to find the value of the function. Now, initial guess simply means x to the power x subscript 0, x naught, right? So this simply means that n is taken simply as 0. So to find our first iteration, we need to plug in the value of n as 0. And if you do that, this equation simply turns as x. Remember, here is n plus 1, and now n is 0. 0 plus 1 becomes 1. So that gives us our first iteration, x1. This is going to be equal to xn here. In place of n, n becomes, of course, is 0 because we're considering when n is 0. So x naught minus, same thing here, f of x n becomes f of x naught all over f prime of x naught, and we have this. So we need to simply obey this formula. First, we know our x naught value is 1.5. Now we need to find the value of the function at 1.5 and find the value of the derivative of the function also at 1.5. So let's do this and see. All right. So we now find f of 1.5, which is f of x naught, which equals f of 1.5. So this simply means we are going to be plugging x as 1.5 in this equation. So that gives us 2 into 1.5 to the power of 3 minus 3 into 1.5 minus 6. So let's see what this gives us. F of x naught is now going to be equal to, so I'm going to point everything all along. So do well to point along with me to avoid calculation errors. So upon evaluation, everything here simply gives me negative 3.75. So it means f of x naught, which is f of 1.5, equals negative 3.75. Also, we find f prime of 1.5. So f prime of 1.5, this is going to be equal to, this is 6x squared. That becomes 6 in place of x. X now is 1.5 squared minus 3. So this simply implies f of 1.5, f prime of 1.5 is now going to be equal to, once again, I'll point everything all together. Do well to point along to avoid calculation errors. Okay. So upon evaluating, f prime of 1.5 simply gives us 10.5. So we have this to be 10.5. Now we need to simply obey the formula. We have x1 to be equal to x naught. So our first iteration, x1 is going to now be equal to x naught, remember, is 1.5 minus f of x naught. We obtain the value here as negative 3.75. So we simply have negative 3.75 divided by f prime of x naught. That gives us simply 10.5. So we have 10.5. So this is going to be equal to, of course, 1.5. Negative times negative here becomes positive. So let's simply find 3.75 divides 10.5. That gives us 0.3571. So we have 0.3571. So if you plug everything together, if you evaluate everything together, you simply find your first iteration, x1, to be equal to, so everything gives us x1 is now equal to 1.85. We have 1.8571. So this becomes our first iteration. Now we have to keep on repeating this formula and repeating the process until the root of the equation converges before we can stop our iteration. So we've gotten the first iteration. Now for the second iteration, that simply means now I'm going to be plugging in the value. Instead of n as 0, n now becomes 1. So in this equation, we'll have xn plus 1. N is now 1. 1 plus 1 becomes 2. That's how we get our second iteration as x2, and that's equal to, so once again, n here is 1, so it becomes x1 minus f of x1 all over f prime of x1. So we simply go back and repeat the procedures again. Now we are simply going to look for f of x1. So we find f of x1, which means plug in the value of x1 into this given function, and we obtain x1 as 1.8571. So this becomes 2 into 1.8571 to the power of 3 minus 3 into 1.8571 minus 6. So if you do this, you simply find the value of f of x1 to be equal to, all right, so upon evaluation, upon evaluating all of this, we'll simply have f of x1 to be equal to 1.2383. So once again, guys, do well to point along to avoid any calculation error. So we repeat the same process for f prime of x. So f prime of x, now this is f prime of x1, simply becomes, to plug in the value of x1 into the derivative. So we have 6 into 1.8571 all squared minus 3. So let's evaluate and see what that gives to us. F prime of x1 is now going to be equal to, so everything here gives us 17.6929 Okay, so we plug into the Newton-Raphson's formula. So x2 is now going to be equal to x1, which is 1.8571 minus f of x1. F of x1 simply gave us 1.2383. So we have 1.2383 divides f prime of x1. This gives us 17.6929. So we have 17.6929. So this implies that x2 is going to be equal to 1.8571 minus, let's find this division. That ratio simply gives us 0.0700 approximately. So this means that x2 is going to now be equal to, x2 simply is going to be equal to, let's find this difference and see, 1.8571 minus 0.070. That gives us approximately 1.7871. So we have 1.7871. So this is now the value of x2. Now, having found the value of x2, we simply plug now into the function, or we simply move ahead to find what the third iteration, right? Now, to find the third iteration, remember the formula is now going to be x3 is equal to the previous value x2 minus f of x2 all over f prime of x2. So this is going to be equal to, we know the value of x2. The value is now what we obtained, 1.7871. Okay, now we need to find f of x2 and f prime of x2, which is the value of the function at x2 and the derivative also at x2. So moving on here, f of x2 is going to be equal to, we plug in the value of x2 into the function, 2x cubed, and x2 is 1.7871. So we have 1.7871 to the power of 3 minus 3x, which is 3 times 1.7871 minus 6. So let's evaluate everything to see what f of x2 gives to us. Okay, so upon evaluating the function at x2, the value simply gives us f of x2 to be equal to 0.0537. So let's find the derivative at that same point. So f prime of x2 is going to be equal to, so we have our derivative to be 6x squared, that is 6. X now is 1.7871 all squared minus 3. Okay, so let's see what this value gives us. Let us evaluate f prime of x2 and see what we obtain. So upon evaluation, f prime of x2 simply gives us 16.1623 approximately. Okay, so having found this, we simply plug now into the formula. So 0.0537, that's f of x, 0.0537 divides by f prime of x, that's 16.623. 16.1623, sorry. Okay, so this means that x3 is going to be equal to 1.7871 minus, let's find out the value of this ratio. 0.0537 divides 16.1623. That ratio simply gives us 0.0033 approximately. So we have 0.0033. So let's evaluate now. 1.7871 minus 0.0033. This simply implies we can now find the value of our third root, x3, to be equal to 1.7871 minus 0.0033. That gives us 1.7837. 1.7838, please. So we have 1.783. So as can be seen, comparing x3 to x2, x2 simply gave us 1.7871 and x3 gave us 1.7838. So correct to two decimal place, this root has converged as 1.78. You can decide to stop your iteration here, or you can still decide to proceed. But let me try maybe 2 more iterations and see if we are going to have up to 4 decimal places converging at the same time. Let's try 2 more iterations. So we need to find the fourth root. Now for the fourth root, the formula becomes x4 equals the previous root, which is x3 minus f of x3 divided by f prime of x3. So all we need to do now is find the function when x is x3. So we find f of x3, and f of x3 is going to be 2 into x3. The value of x3 is 1.7838, 1.7838 to the power of 3 minus 3 into 1.7838 minus 6. So let's evaluate everything together once again to obtain a value. So upon evaluation, we have f of x3 to be negative 0.0055. Let's also find the value of derivative at that point. So we find f prime of x3. This is going to be equal to, our f prime give us 6x squared. That becomes 6 in place of x. X is now 1.7838. 1.7838 to the power of 2 minus 3. So let's evaluate everything together to obtain f prime of x3. So this gives us approximately 16.0917 approximately. So let's plug these values into the formula. We can now find x4 to be equal to x3, which is 1.7838 minus f of x3, negative 0.0055, divided by f prime of x3, 16.0917, to divide 16.0917. Okay, so this is going to be equal to 1.7838. Of course, this becomes plus, negative becomes plus. Let us find this ratio. 0.0055 divide 16.0917. Okay, so this is approximately 0, because we have just 0.000, so it's approximately 0, right? All right, so and if you add that up together, this simply implies that x4 sorry, is still going to remain what? 1.7838. Okay, so if you compare this with the previous root x3, you see that correct to 4 decimal place, the root of the equation has simply converged. So the answer to this particular question is simply what? 1.7838. This becomes the root of the given equation. Okay, so you can stop your iteration here. All right, guys, so that's how to employ the Newton-Raphson's method of numerical methods to solve engineering mathematics problems. I will see you in the next video. Cheers.